Welcome everyone to UCSD CSE 291D 234 Data Systems for Machine Learning. My name is Arun Kumar. Today we have an exciting invited guest lecturer from industry/academia, Dr. Matei Zaharia. He is an assistant professor at Stanford University and also the chief technologist at Databricks, which is the commercialization of Apache Spark, which Matei started in his PhD work at Berkeley. Matei, of course, needs no introduction in the data science, data engineering, ML engineering space. He's done a lot of spectacular, high-impact work, so it's really our privilege to have him here come meet with our students and give this guest lecture on MLflow, a very interesting new platform for productionizing machine learning that has been seeing a lot of adoption, especially among enterprises. So we'd love to hear from Matei about that. Protocol for the lectures, this whole thing is being recorded and Matei has consented for this being made publicly available. So apart from being posted on Canvas, this whole recording will be posted on YouTube as well. So please plan accordingly. Questions, Matei, would you prefer questions during interrupted or to the end?
I think it's okay to have some questions during the talk too. Yeah, okay. If it makes sense, right? I only have, I think, maybe 45 minutes max of slides, so there'll be plenty of time for questions, but feel free to ask throughout if you want.
That's great. So students, if you want to ask a question, please raise your hand. I'll be monitoring and then I will try to pause Matei and then ask the question. And then you could also unmute and ask it yourself. So without further ado, let's hand it over to Matei. Matei, please take it away. Thank you again for joining us.
All right, yeah, thanks a lot for having me. I hope this is interesting for people to see. So I'm going to talk here mostly about my experience on the industry side with enterprise companies that are using machine learning, but I'll try to talk about it a little bit from more of a research and CS perspective to understand what kind of problems they're solving and why they're developing these new kinds of systems, including MLflow, and also what some of the open questions are in this space. So, but that's sort of the background for the talk. So I'm going to start by discussing the top challenges of actually applying ML in industry as we see through Databricks primarily. And then I'll talk about machine learning platforms as an emerging abstraction. Chances are if you talk to anyone at a company that's seriously using machine learning, they will say that they have or they're building a machine learning platform. So it's a concept that they're all thinking about. Same way that everyone had a data warehouse or these kind of things. It's definitely an abstraction that's coming up. And I'll talk about MLflow, which is an open source machine learning platform that we launched at Databricks in 2018. It's hosted at the Linux Foundation. It's an open source project with many other companies contributing, but it's meant to tackle some of these problems. And finally, I'll talk about some interesting use cases of it among customers, including surprising ways that they're using it that came out of the requirements for using machine learning in industry that we hadn't really thought of at first, which might be interesting for people doing research. And maybe I'll talk a little bit about ongoing work and some open questions as well. And yeah, as I said before, feel free to ask throughout if you have questions or something's unclear. I'll also have time at the end because I can't see all the faces on here, so you can just ask stuff. I guess I'll also view my chat, so you can maybe ask things in the chat if you don't want to interrupt. I will be able to see the chat.
I will also be monitoring the chat just in case.
Okay, great. Yeah.
Pause point where I can pause you and ask the questions. I can do that too.
Sure. Yeah. Okay, great. So yeah, so all this is based on my experience at Databricks. So I'll just briefly a little bit about it. Databricks is a data and ML cloud platform company, and we started in 2013, and it's actually grown quite a bit now. I think we are one of the largest, cloud and data ML services that are available in the public cloud, definitely on the same scale, and in many cases even larger than some of the cloud providers' own products in this space. And we have about 7,000 customers of various sizes. And overall, we run workloads on several millions of VMs at a time. And we have hundreds of thousands of users on the platform, engineers, data scientists, analysts, and so on. And customers are doing a variety of things with it. So it's not all ML, but quite a few of them are doing machine learning as well. So some of the ones that are doing machine learning you can see there. And we're really targeting enterprise customers across industry. So it's not tech companies necessarily, although there are a few of those, like you see Adobe and HP, but it's also many other organizations that can collect data sets and build applications with machine learning. So that's kind of what we're targeting. So one thing that I think we immediately see when we look at our use cases is that machine learning is being adopted for really critical applications at these companies. It's already out there. You sometimes read articles saying that machine learning adoption is still very nascent and so on, but most of the companies we talk with already have something in machine learning even before they start using Databricks. And of course, it's being added to more and more applications across time. But one of the big differences you'll see even from these kind of web companies like Twitter or Facebook is that these applications can be really critical for that company and can have a lot of negative impact if they go wrong. So just as some examples, so Nationwide is an insurance company. Its whole business, the core business of Nationwide, is to create insurance policies that will be profitable for them without incurring too much risk. That is its whole business. So it is basically like the whole business is doing statistics and pricing things and modeling things. It's not like machine learning is a side project. And so now they're looking at using machine learning to price a bunch of their insurance policies and also bringing in much larger data sets and querying those when creating these pricing models. And so that has to work very well and in a dependable way, because otherwise, that whole business is going to go bust if it's not pricing its policies properly. And they've been doing this for almost 100 years now, doing insurance, that is. Another example in the industrial space, so companies like Shell and other companies are managing these large-scale industrial processes using machine learning. So for example, in Shell, they manage inventory, and they also manage supply chains as they're ordering parts. And these are for things like chemicals, where you can't actually store an infinite amount of a chemical somewhere. It's expensive to do it. Bad things might happen if you don't have a supply chain that flows well. And so it has quite a bit of impact on the company's costs and revenue overall. And a final example that's very common is any kind of financial company or bank. So in HSBC, for example, they're using machine learning for fraud detection and also for personalization, and they have 170 petabytes of data of various types about transactions, other information happening. And so they want to be able to use all that. And the other interesting aspect here is they also have to be compliant with regulations in many different countries, where they have to show that they're not using an illegal kind of data to, say, price people's mortgages or something like that, because otherwise they'll be sued for doing that. So that's where the machine learning has to work in this highly regulated context. Okay. So ML is being used, it's very critical, but at the same time, it's also very different from traditional software, and that makes engineering ML products and then actually operating them in production pretty challenging. So let me talk a little bit about how it's different from first principles. So the first thing to look at is just what is the goal. So in traditional software, you're building like a web application or something like that. Usually the goal is to meet a functional specification. So for example, when I click this button, you have to create a new file. And when I press this other button, then so-and-so should be able to view the file, but this other person shouldn't be able to. So it's sort of a Boolean condition. It's either it's working or it's not working. And it's relatively easy to test for, and that you can just check whether it's meeting that. If you do have to design a bunch of test cases, you can just kind of check whether it's done it. And then once you've met the specification, you're done. If you don't touch that software anymore, it's going to keep working. Now, in contrast, in machine learning, the goal is usually to optimize some kind of metric, for example, prediction accuracy. And there are a couple of interesting properties here. One of them is you're never like truly done. There's probably always some way that you can make the metric better. And, for things like pricing your policies or whatever, each improvement you make will lead to a very large impact on the outcome. So you need to keep optimizing this metric over time. The other interesting factor is that the application will kind of decay if you stop working on it, if you stop updating it with new data. So that's one of the core differences. So on the left, it's kind of a project you build once and then it's sort of okay in a stable state. On the right, it's something that has to continue on living and being maintained ideally in order to perform well, and something where you might constantly want to experiment to make it even better than what you have today. Okay, so that's one difference. So the second difference is what affects the quality of the results. So with traditional software, the quality pretty much only depends on the code in the application. So that means if you have lots of engineers review the code, then you're pretty sure that it's correct. And also the code is not necessarily that large. I mean, it can be hundreds of thousands of lines of code, but people can kind of look at all of it. And once they think it's good, it's probably okay. You can check whether it's working. In machine learning, on the other hand, quality depends heavily on the input data, because machine learning is programs that generalize from data. And it also depends on these more auxiliary parameters, like tuning parameters, that you have to think about as well. And the interesting difference is that, even though you could review all the code in the application, you probably can't manually review all the input data when it's in the terabytes or petabytes of data. So that already poses an interesting problem. You now have to use some kind of analytics tool to slice through the data and see what's happening in there. And usually, the data is also changing over time, which makes it worse, because with your code, you can stop changing it and you're pretty sure it'll keep working. But here, your application might not work on tomorrow's data anymore. So that's a second difference. And then the third difference that's kind of interesting has to do with software engineering and the kinds of tools and systems involved. So with traditional software, you usually pick one software stack and you're done. For example, you say, okay, we have to build a new application. I'm going to use whatever Node.js to program the web part. I'm going to use, MySQL as a database. Maybe I'm going to use like React for a user interface. You pick, one element for each part of the software stack, and then that's it, and you're done. In machine learning, because you're trying to optimize this metric, and any improvement at all can have a huge impact on your success, you want an environment where you can actually compare and combine many different libraries and algorithms for the same task. So nobody does machine learning, for example, by saying, oh, I'm only going to use TensorFlow for this application. Let me just code it up, and that's what I'm going to use. They're going to constantly be looking out and seeing, hey, some algorithm just got published for this problem that runs in PyTorch. Let me try that. Someone posted a data preparation routine that's coded up in R. We think that it will help clean the data and make the model better. Let me run that as well. Maybe the whole thing, you want to compare it with, with some other approach, like a decision tree or whatever. So unlike traditional software, you don't want to limit people to running only a small set of tools. You actually want them to be able to try anything new that gets published or that they think of, and easily see how it would change the results of their application. Okay. So these are just some of the top level differences, and you'll see how they lead to a very different engineering process and tools around that. The other thing to think about is productionizing. So I hinted at this, so like building the application once isn't enough. You also needed to keep working continuously. And that means you need to update it with new data and retrain the models in it and redeploy them to make sure that they're working. And then the other factor that makes production harder is that often there are different people in an organization that are responsible for these parts, because you don't have, it's hard to have one person who's an expert on everything from the data engineering to modeling to actually deploying the application. So you need to make sure that the handoff of information and code and so on across these people works well as well. And often there are problems when it doesn't work. When, for example, the type of data you got during training looks different from the data you get in production because the application developer is feeding it in a different way or something of that form. So it's really important to design infrastructure where all these folks can collaborate on it. Okay, so these are the problems, and as you can hopefully see, it's pretty difficult, and you know, quite a few things can go wrong, and when they do go wrong, they will often go wrong in subtle ways that are hard to debug, because you'll just see a result that's worse, like a worse accuracy. It's hard to tell why that's happening. So that's why there's this solution emerging, this abstraction of ML platforms, which is now quite widespread. So this is software to manage the ML development and deployment process, all the way from data to experimentation to production. And some examples of these are platforms like TFX, FB Learner, and Michelangelo at all the large tech companies. But in fact, we found that most enterprises who seriously use ML, like the ones I mentioned before, are also, you know, internally building or managing some kind of ML platform. And these platforms are really successful, especially these large ones in the large tech companies. Each of these companies have hundreds of applications that are built and managed using these platforms. So they do make it a lot easier to build these. So it's an interesting thing to study, to figure out how do we design, you know, the best ML platform for, you know, for various use cases. And what the concerns in an ML platform differ. You know, I don't think there's a clear definition on everything that should be in there, but they could include things like data management, experiment management, model management, deployment tools so you can do inference, reproducibility, testing, monitoring, you know, many other things could probably go in there as well. But the key part is that you want them all to happen through a consistent interface where, you know, many users can write applications and collaborate and, you know, deploy them and maintain them once they're built. So that's basically what needs to go into it. Okay, so we saw this this trend around 2018. And at the time, we saw that each company was largely designing its own platform. And often it was doing that with limited scope because it's only one company building it. So for example, in Google TFX, it's just for TensorFlow because, you know, that's the main thing they wanted to support. Or many of these platforms had only specific deployment environments, like only Kubernetes or on AWS. Because, you know, that's what that company has. And one of the other problems is that the ML platform team often became a bottleneck in the organization because undoubtedly there would be someone who goes in there and says, can I use PyTorch instead of TensorFlow? Can I use R? Can I use XGBoost? And so on. You know, as I mentioned earlier, it's really important to allow that when your goal is to create the best model possible, as opposed to just a model that sort of works. So that's what was happening back then. So we asked ourselves as we were going into this space, can we provide the same benefits with an open platform where hopefully many companies can collaborate and build something together that's still, you know, customizable enough for each one to use by themselves, but where they don't have to do all this work from scratch and be a bottleneck trying to add new things into the platform. So that was our approach to this to try to make it a very good platform, basically. And so that's what we did in MLflow. It's an open source ML platform, but more importantly, it's based on what we call our open interface design philosophy, which is we want to make it very easy to combine arbitrary ML code and tools that you have, including custom tools inside your company that are proprietary, and put them in the platform and use them together. And to make that happen, we had a few ways that we did that. So we tried to design it around these generic APIs that can be used from any programming language in every environment. So most of it is command line interfaces and REST APIs rather than something specific, like you got to import a Python package and you can only use Python. And also we tried to make it so that at each step it's easy to add in it's easy to add MLflow to existing software you already have in your company. If you already have a machine learning application, you don't need to throw it away and write a new one in MLflow. You can just add a few lines of code and start getting a lot of the benefits for MLflow. So that's sort of the design philosophy. I'll show how that comes up later on as I talk through it. But that, I think, is one of the most important things to get right if you want this to be successful. If you don't do it, then users might never adopt it because it's too much hassle for them to switch onto the platform and to connect it to their own tools that they already have. And then it's much less valuable for them. So what's in MLflow? So it's actually got 4 components at the moment. It's got MLflow tracking, which is for tracking experiments and metrics, basically visibility or logging for your machine learning workflow, but in a way that makes it easy to do machine learning specific queries and visualizations on the output. That's probably the single most widely used component because it's the one that a lot of people start with, and it's meant as an easy way to immediately add value to existing code you have. Then there's MLflow projects, which is a way of packaging your code for reproducible execution, which is useful when other people have to deploy it and maintain it, or when they want to build on it. There's MLflow models, which is a format for packaging your models, regardless of what library they come from, and for deploying the models to many different tools. So you don't have to write a custom deployment script for each one. I'll explain how that works. And finally, there's the model registry, which is a collaborative environment, kind of like a GitHub type interface for model management, where you can publish models, update them, document them, and have applications that pull out the right version of a model. So I'll show how all of these work. And there are also a lot of built-in connectors, many coming from non-Databricks contributors to many popular machine learning libraries and services. And there are even more that just have it integrated into their own library. So it's definitely achieved this goal of being easy to connect to a whole lot of different services. So that's what's in there, and I'll talk about it in more detail about how it looks. And since we started the project, it's also grown quite a bit. So it's a pretty large open source community now, and I think it is the largest overall in terms of open source ML platform projects. So we have over 2 million downloads per month on PyPy of the Python package. We have 260 contributors. Our team working on it is maybe like 15 to 20 people who've worked on it over time. So definitely a lot of non-Databricks ones. And the usage is going at about a factor of 4 year over year. And on the Databricks cloud service, we have more than 1.5 million experiment runs per week. And many other companies have also integrated MLflow into their products. For example, Microsoft with Azure ML, RStudio, Splice Machine, quite a few other platform companies as well, and of course, various users. Okay, so that's a very quick kind of overview of it. So next, I'm going to go into more detail about how it works and how we followed through that open interface philosophy. And then I'll talk about some of the use cases, especially some of the more surprising use cases. And definitely let me know if you have questions at any point.
Okay, so this is a good pausing point for the audience to have any questions.
Yeah, I see some in the chat. Let's see.
I don't.
Okay, so I see a private question in the chat for someone. Let's see if it's actually, it's okay if I say this question.
Yeah,
so the question is, I'm wondering if ML platforms are mostly used by the machine learning team, for example, Google AI or Uber ATG, or across all the teams at a company? And is it the trend that all giant companies have their ML team, or is there just like one ML team that like, is there a separate team for each project, basically? So yeah, so people organize this in different ways, but the ML platform products are also meant to be used by application engineers and by data engineers who push the data going in. So it's not just the machine learning developers themselves, but depending on your setup, you know, there are different ways to organize your company. Like some companies have a centralized ML team where, you know, they decide on a roadmap and that team handles all the projects and maybe also owns all the infrastructure. Other companies have separate teams for each project. And in some cases, the ML engineers are embedded into a product team. So like, for example, the team that does whatever, like newsfeed at Facebook, maybe it has its own ML engineer. So there are different ways of organizing it, but in pretty much all cases, you do need to collaborate with other teams, the ones that can collect data, or with other people at least, whoever is collecting data and whoever is deploying the model. Other questions? What is the main user of ML platform? Yeah, it's all of these users I showed before, actually. Let me go back on this plot. So the data engineers, ML engineers or data scientists, and application developers, they'll all use it in different ways. How important is adversarial robustness in the ML model lifecycle? I actually haven't seen that too commonly as a concern. And I think part of the problem is that none of the defenses in research like actually work that well. I mean, some of the ones that have provable guarantees lead to very bad quality for the model. So I think users are not really trying to put these models in, in settings where an adversary could attack them. Or at least they're not making them mission critical there yet, because adversarial robustness is not that good yet. But hopefully it will get better. But certainly a lot of use cases like these fraud use cases I talked about, the whole name of the game there is that, people are trying to sneak stuff by. So you do need to find when there are strange things happening and then to automatically detect them. So there are adversarial settings. It's not by perturbing pixels in an image, or, not necessarily, but there's definitely people trying to hide stuff. Cool, yeah, these are good questions. How competitive is the market for ML platforms? Are there lots of products or only a few? So a lot of companies are building, things that cover parts of the ML lifecycle, and sometimes they try to cover all of it over time. So it's definitely an established concept. It's still early on. There's a lot of design, to figure out. Like, I don't know whether anyone has the absolute, like anyone knows what the design is. It's not like, what's the market for whatever, like a transactional database where it's like very clear what the product should look like. This is still a new kind of thing. And I think there's still innovation in terms of the interfaces and, the components of the platform. Cool. And then I guess I see one more question. Is the app developer mainly working on ML algorithm deployment or on other things? So this app developer here would be someone who builds the actual application. So like, let's say you're building an app to run on a smartphone, right? That person is coding stuff up in Swift or whatever they're using. And they also have to put a model into it and feed it the right kind of data and get it to work. So that's what I mean by app developer. They're actually building the whole app. They're not just trying to deploy a model or test the one model. They're trying to integrate it into some kind of application.
Okay, Matei.
Cool.
Thanks again for answering all these questions. To the audience, I mean, it seems like you can only post questions to either of the co-hosts. Feel free to.
Yeah, that's kind of weird. Yeah, but it's one of the many Zoom security settings, I guess.
Yes.
Too bad you can't post to everyone.
Yes.
Cool. Okay, but yeah. Yeah. Let me know if someone posts questions to you. I'm just looking at the chat, and
Okay.
I went through all the ones I saw. Cool. Okay, great. So that's okay. So that's very quick overview and the design philosophy. So next I want to talk in more detail about some of the components to see how that manifests itself and some of the concepts in there. And then I'll talk about some use cases. So let me start with the tracking component. So the point of this is to get visibility into experiments and also into production runs of your application once you're running it, continuously, like to update your model. And the idea is very similar to logging or monitoring in traditional software, but we've got basically a schema for the information being captured and a set of visualization tools on top that are specific for ML and that make it more powerful for that purpose. So let's start by just doing experiments and designing a model. So definitely the most common way to experiment with ML is to just write a bunch of programs, and you can have whatever code you want in there, and then you would have something like print statement, some ad hoc way of logging the results. So you can do that, and you'll get something like this, and you'll say, okay, I tried a bunch of different parameters, and here are the accuracies I got, and maybe you'll get to a good model. But as you're doing this, and trying to keep track of your workflow and compare the results, you can often run into a lot of problems. So for example, what if you start tuning some other parameter that you weren't logging before? You got to remember what you had set it to and then change it and maybe change all your logging statements. What if you change the version of your ML library? Maybe the code doesn't change at all, but with a new version, the results are actually different because they fixed a bug or something. That can be very hard to debug if you didn't realize you did that. And as you see your historical results, it's hard to link back to what version of the code and environment was each result from. So it's quite hard actually to keep track of your process and get reproducible results and share them with people or get someone else to productionize your work once you've built it once using these ad hoc methods. So that's where MLflow tracking comes in. It's a set of logging APIs that will capture a lot of information about your compute environment and your results just as you're running the code. So for many libraries, there's actually this auto log interface. You just have one line of code and we intercept calls into that library and we log as much information as we can about it. We also log information about your just the environment where you're running the code as well. So you can just run that auto log function. If you want, you can also log custom information. There are these lower level APIs to do custom stuff. So that's how you can, if you have your own proprietary code, you can use that. And when you do this, this information will get sent to a server and you can, or it will be saved in files on your local machine if you're running in local mode. And you can just run this UI command to see a UI for it. And on the UI, you can see various information, parameters, metrics, output file, code version, and so on for each of your experiments. So what can you do on it? So you can take these runs and sort them. You can click on one and view stuff in it. You can log arbitrary files actually with your model if you want, or with your run. And you can also take notes on these things as you collaborate with people. And then the other thing you can do is you can compare two of these runs or more. You can select a bunch of them, compare, and see what was changing. And you can actually visualize, how different metrics correlate to each other and so on. And all of this has APIs as well. So you can also do this programmatically if you want. You can set up an automated system that will keep track of your best parameters. Or as you do a production job, you can set up an automated system to monitor it and to see when things are going wrong. So very simple, but it's really powerful to be able to collect this data and query it. And this is why this is one of the first things that people get started with, to structure the development process. Okay, so that's tracking. So the next component, projects, this is a way to package your code so that it's easier for other people to run. So it's also very simple and generic, but it's quite popular as a way to organize your workflow. so basically, this is just a self-contained description of what you need to run a program and what its parameters are. And inside your project is just a Git repository or a folder inside it. And you have this special file, the ML project file, that describes the dependencies and also describes the entry points that you can call in the project and the parameters for them, and how to run it. And so this is a generic thing. Your command, in this example, it's Python, but the command could be, you know, something with a totally different programming language. It's just a script to actually run that. And the nice thing about it is that for the consumers of the project, they get a uniform interface to run it regardless of how you wrote it. So they can run it on the command line with just MLflow run and then the URL of the project. They can also specify a version. And they can also run it programmatically, and MLflow will set up the right environment for it. It will download the dependencies like the conda dependencies here, and then it will run that code. And you can also hook these projects together programmatically into multi-step workflows just by using this MLflow run function. And the tracking UI will actually show you which project called which other projects. So you can see the output from each of them, the parameters and the metrics and so on. So that's the projects component. And this is really nice both for handing your code to another machine learning engineer who's trying to create new models, or for putting it into production to get a reproducible environment. Cool. I see a question here. So about tracking, will the tracking make ML training slower? Not really. Not compared to the cost of doing the ML training. Logging this stuff is not very expensive in pretty much most cases. Yeah. Yeah. So that's.
Matei, I have a question at this point. I don't, maybe if now or later on is fine too.
Yeah, go for it.
What about the data set aspect of this? So you mentioned like people do data prep and cleaning and transform the data.
Yeah.
Will MLflow help track that? Do you do data set versioning? Do you do like feature extraction? Can they register that somehow?
Yeah, that's a great question. Yeah. So actually, I didn't talk about that, but you can do that in a few ways. So the easiest way is if you make your data preparation steps be projects like this, then as the projects run, they can output, as you saw in here, they can output arbitrary files as artifacts. And you can also output like your prepared data set as an artifact. Mm-hmm. And then you can set up the next project to like read the output from its parent. So between these workflow steps, you can pass data that way. But these are like immutable artifacts. So each project ran and it created a new artifact. If you want a mutable table or something, we don't model that directly now. So you have to figure out how to do that yourself. But we have a pretty nice integration with Delta Lake, which is a way to have versioned Parquet tables, basically. And in that one, we record which versions you're using, and we can tie that into your MLflow tracking for that run. And then you can easily find the version that was used.
Got it. And so the Delta Lake will take care of sort of view management and materialization management and stuff like that? Or do they have to force create every version of the file that is produced? So
in Delta Lake, it basically does copy and write whenever you change the table. So it can easily reproduce old versions if you didn't change much. If you changed everything, then it will be storing every version.
Got it. Okay.
Yeah.
I have to see a chat question. Just the question asks, did you consider a data registry in addition to a model registry, especially for reusability and reproducibility of key goals?
Data registry? Yeah, the way, so basically, so it is an important thing. The way most of our users are solving it is using external software for that purpose. So Delta Lake is one. If you just manage, if you have like a data lake type setup, so like storing something in in Amazon S3, for example, then that's the most common thing. There are some users who use DVC, which is a software for data version control. But data often, like in an enterprise at least, they already have a way of managing data. So we didn't want to tell them to move their data to something completely different, because that's very expensive. and also becomes kind of a management nightmare to have to copy the data and so on. So we don't have a built-in way like where you have to put the data in it. But we do want to have, I'll show the integration with data versioning, and we want to have richer ones. And I think it's a nice question of how do you integrate this in other data systems cheaply. There's also this whole concept of feature stores I'll talk about, which is, when you're designing a data store just for ML. Yeah.
So Matei, just to clarify, does that mean like the data sets can reside on any data warehouse or database system that people use, and then MLflow can still be working?
Yeah, you can still read them, but it's not as smart about recording what you're using as it would be for built-in things. So you have to manually record that information, like for example, as a parameter for your job or whatever. Yeah, it does log the parameters of each of these workflow steps, for example, and you can also log custom things. So if you write, for example, you can write a job that does a transformation on any given input file, and then when you run it, will remember which file you ran it on.
Got it.
Yeah.
Great. Thanks. Let's proceed.
Yep. So yeah. So these are these are like 2 steps. So now we can track information about our runs, and we can make them reproducible and make them easy for someone to deploy in production. So that's a good start. So then the other 2 components have to do with models. So these are actually a little bit maybe different from other things you might have seen. So I think they're interesting to look at. So the first one is the model packaging format. So it's a generic format to package and deploy models from any library. So this is interesting because there have been a lot of proposed formats to save models, and most of them are focused on saving the weights in some way. So for example, Onyx is one that is meant to store neural networks, and a whole bunch of libraries integrate with it to various extents, and then you can push these weights into some kind of accelerator device and do inference with your neural network. But what we wanted for MLflow is we wanted to be able to package any kind of model you have, maybe even from internal libraries in your company that were built, were written before Onyx existed. And we wanted to expose it to, as many deployment tools as possible. So we actually created this format that's very simple. It's just a bunch of files and a little manifest to describe them. And inside it, you can list different flavors, which are different interfaces for reading the model. And these can include existing interfaces like Onyx, but they also include more generic things like just here's how you would run the model as a Python function. And then based on this format, there are also many connectors in the open source project to deploy your model to different environments. So you can take the same model and deploy it in a Docker container for real-time serving, or you can deploy it as a user-defined function in Spark SQL for batch and stream scoring, or you can pass it to interpretability tools and so on. So that's what this is about. So how does it look? So, it's a pretty simple kind of file packaging format. You've got a directory, and you have this manifest file that describes some info about the model, and then you have arbitrary files for whatever you're saving. So this one is a TensorFlow model, and you'll notice there's some information. There's the experiment run ID, which is nice for tying it back to that tracking user interface that I showed. You also have the time when you created it. And then you've got these flavors that let you read the model using different protocols. And it's easy. Users can even create their custom flavors if they want. And then there are some built-in flavors that the rest of the things in the rest of the code in MLflow understands. So what this one means is, if you have a tool that knows how to load TensorFlow models directly from the protobuf format, for example, TensorFlow serving, then it can look at these fields and figure out how to load it. But there are also many tools that don't know anything about TensorFlow, but still want to run a model. So any tool that can run a Python program can actually use this Python function interface, which just says, hey, here's a Python module you have to call in order to load the model. And then it can use it. So for example, if you want to run this model in a Docker container or in Spark or whatever, we just have to write a way to run to load a model, to run a Python function on your data, and you can load the model as a Python function and just run it in there. So once you've got this, there are a bunch of built-in APIs to actually use the model, and there are also integrations in a lot of third-party products like Celdern and Amazon SageMaker and other tools like that. And in all of them, you just give it, you pass a run ID, or you can pass a URL to a model, and it can start running that in that interface. So that's the idea here. So it's about portability. It's a little bit like a Docker image in some way, but unlike that, it also lets you expose these other flavors for tools that actually do understand the weights. And the cool thing about this is, again, if you think about your application engineer, they don't need to do a lot of extra work when the ML team changes from using TensorFlow to using PyTorch, because they still run one of these commands. They just run serve this model or load it as a Spark UDF, and they don't need to know about the internals of the models. So that's basically the goal here. Okay. And then the final component, and so I wanted to show is the model registry. So this is this environment for managing and reviewing and sharing models. It's inspired a little bit by tools like GitHub and just software development tools. And so the problem here is how do you share models inside a large company? If you just have files sitting in a directory, or you're emailing them around, or you're checking them into Git, none of those approaches are super nice, to work with, and it's very easy to have someone using the wrong version of the model and getting the wrong results. So the model registry is this service with a user interface and APIs for these different groups to interact. So a developer can push versions of a model into it. Reviewers or automated tools can listen to events in there and then run tests on the model and tag it with extra information and basically just check how it's doing. Very similar to how, when you submit a pull request on GitHub, you might get automated tools that run tests. And then downstream users can load the model, and they can make queries like, for example, give me the latest version of this model that's marked as production, or that has a specific tag or whatever, and then they can use just that one. And as the developer updates the model, they can automatically pull the latest one. So this is the continuous deployment part of it. Okay. So how does it look? So this is just the interface. So at the top level, when you go into it, you see a list of models, and inside each model, you see a list of versions of it, and you can also have a description of it that you can change. And you'll notice that these versions have their own life cycle. So for example, some version is in production. Some versions are archived because they're old. This version is in staging, maybe this version isn't in any lifecycle stage. So we have this concept of stages for each model. And then once you publish a new version in there, by default, it starts in no stage. You can, as a user, you can request a transition into a different stage. So request transition to production. And then this is going to allow the owner of the model to review it, or you might have automated tools that listen to the model and they automatically test it. And in this case, I'm also the manager of this model. So I also see maybe a transition, and I can approve it or reject it, and I can leave a comment on it. So that's basically the way that it looks. And as a user of the model, you can just request models/airline delay Spark ML/production, and it will always load the production version. And if your app is loading that each time it runs, it will automatically be updated with the one that you wanted to pull. So that's kind of a quick look at it. And then within it, again, following on the open interface philosophy, we also allow you to customize the kind of information you track about models and to search for it. So you can add tags to each model, which are just key value pairs. For example, maybe you have a human review process, which is to check if the model passes GDPR review. And you also have an automated process that does a performance test. And you also have a search API that lets you search across many models and, for example, find all the ones that have been uploaded recently and test them and push new versions. So because of this, enterprises can connect this into the very custom processes they have. And as I'll talk later, there are quite a few interesting ones there. Like if you're doing a model for for banking or for a medical device or something like that, there are all kinds of people who have to check off on it and review it. And you can design a custom process here, much the same way you can do that with tags on pull requests inside something like GitHub. Okay. So these, this is kind of the last component, and this is also, I would say, this is probably kind of the second most popular use case of MLflow beyond experiment tracking, is to set up a model registry. Of course, as part of that, you'll also use tracking and you'll also use the model packaging format. But this abstraction of a model registry is very powerful to let users and automated processes collaborate on these models. Okay. So at this point, I think, yeah, I can answer a few more questions. I see some of them in there, but I hope this has given you a good sense of the platform. And you'll see with all the things I showed, you can use any machine learning library you want. And there are also a ton of ways to customize it, to add custom tags, custom parameters, and write your own tools on top to search across it. So that's kind of this design we were going for, where every organization can easily adapt this to their own requirements because everyone has pretty unique requirements. Okay, so I see a couple of questions. And let's see. So does the app developer know the pros and cons of each model as they're working with the registry, and how do they know which one to use? So yeah, so the nice thing here is the deciding which model is in production can be done by these folks, and then the app developer can easily write code that always queries for like the latest production model and loads that one. So it depends again on how you want to organize it. You might want a workflow where the app developer reviews each model and tests it, or you might want a workflow where maybe someone wrote a script to test the model or something, and people are just publishing these versions and they automatically get tested, and your app code always loads the latest one. But basically inside in the registry API, there's an easy way to say, I want, for this model name, I want to load the production version. And there's also an API to say, for this model name, I want to load a specific version. So for example, if an app developer wants to lock in their app at version 3, they can say, okay, load airline delay /v3. But if they want to say, oh, I actually want to use the production one, they can do airline delay /production. It's a lot like maintaining branches of a code repo, for example, and deciding which branch to deploy automatically. Cool. Okay. So yeah, so I hope it's given you a sense of the overall platform. And how these things come on. So next, I'm just going to talk a little bit about how people are using this and some surprising things. And definitely feel free to ask more questions throughout this. So yeah, when we launched this, we weren't 100% sure what would happen, because ML platforms are still a new concept, and we had this design where it's meant to be this open interface design. But fortunately, we got a lot of users right away, and it does provide a lot of benefits to these users. So there were quite a few of like what I'd call expected use cases, things that we expected people to do. Pretty much all the things I talked about before: tracking experiments, doing model design, tracking performance of continuous jobs. Once you've deployed that training job to update your model, you have all the tracking info in there. So now you can just see it and query it over time. Deploying the same model to different environments like batch and real time through the MLflow models package. Running pipelines deterministically, and also continuous integration and deployment. So automated software deployment and testing using stages. So these are all common things. And companies of all kinds are using them. I just put some examples of companies that talked about it publicly, but I'm not going to go into tons of detail, but these are each companies that are managing multiple models, sometimes hundreds of models with MLflow, and keeping track of a lot of information. So, for example, in T-Mobile, in this ad fraud detection use case that they're talking about, finding out when people who click on an ad are actually fraudulent, they're looking at over 200 different metrics to keep that model working well. In H&M, they have, the point is to make these data scientists productive so that they spend more of their time on model development instead of tuning and monitoring. So they automate, once you package your code as a, MLflow project or something with parameters, you can easily kick off, lots of versions of it and see how they're doing and monitor them and select the best one. And then ABN AMRO, which is a bank in Europe, they have over 100 models that they're deploying using MLflow. So these are the kind of expected use cases, but there are also some really interesting use cases that we hadn't expected, but that definitely makes sense given the context, and they show you some of the power of this, this platform and API-oriented approach to managing ML. So one of the first ones that was surprising was companies who want to manage a massive number of independent models for the same task. So for example, a company might want to train a separate model for each of its facilities, like let's say each factory or each chemical plant that they have, or even each chemical processing machine for each of its customers, and so on. For each geographic region. So this is seems a little bit weird in some ways when you think about what ML is supposed to do, because you would think that by pulling together information about, say, all facilities and all customers, you would build a better model than training something separately on each one. But there are some benefits to doing this. So it avoids interference across these entities. So for example, if you've got your chemical processing machines and you're trying to predict when, how quickly each of them will work or something, you don't want like bad sensor data from one of the machines to corrupt the model that used to predict all the other ones. Also, the machines might be subtly different, and because they're running in different environments at different temperatures, whatever it is. So it might actually be easier from a modeling and kind of fault containment perspective to say, look, I'm going to train a separate model for each machine. Each machine is anyway producing, many gigabytes of data every day of telemetry. Another interesting reason is privacy and compliance. So for example, there's a large enterprise software company that's a customer, and they allow teams at their customers, for example, marketing teams and sales teams and so on, to keep track of like what's happening and decide who to reach out to about promotions or about selling something. Now, in this environment, imagine that both like Pepsi and Coca-Cola are your customers. It would be really bad to learn some model based on the behavior of, like, say, sales reps at Pepsi, and then recommend suggestions to Coca-Cola based on it, and say, because Pepsi is talking to this restaurant, like maybe you got to talk to them too, because otherwise you'll lose the contract or whatever. So it would be very bad for them to do that. So they have like tens of thousands of customers, and they need to train a separate model for each customer to ensure there's no interference. And the same thing might happen due to legal reasons, like data about this user should not leave their country or something like that. So it's a pretty interesting use case, and it's come up in predictive maintenance. It's come up in energy grid. QB is this company that tells you about your home energy consumption and what you can do to reduce that, basically. And it's come up in this enterprise software company space. So how do you solve this? So the solution is sort of what I'll call hands-free ML, where you have a script that runs, that kicks off the training of each model, and then you have tens of thousands, maybe millions of models actually being trained, and you need to query them using parallel analytics, like using an analytics tool. You can't manually inspect each model. So in many of these use cases, they actually train each model using an AutoML library because they want to model each time series or whatever it is as well as they can. They don't have time to tune the individual ones. And then once they train them, they use the MLflow API to query the experiment metrics and to analyze it. So for example, we have a nice API for loading all your metrics into pandas or even querying them with SQL from Spark SQL. And then you can do things like figure out what are the worst performing predictions or whatever, and you can debug those as opposed to wondering about all of them at once. And finally, they'll do batch or online inference with the models. And again, having an API that lets you say, what's the latest, model that's marked as production for this facility or whatever is really nice for that. So it's an interesting use case that I think is going to be around for a while because it's just, it's a nice way of modeling stuff if you want to ensure privacy and non-interference among these things. But you need an automated system to do this. If you write this from scratch, you're going to have to, reinvent a lot of the things that, that we're doing automatically. So that's one kind of cool use case. And then another cool use case is actually experiments beyond machine learning. So all the stuff I talked about with keeping track of the dependencies and data that went in and being able to collaborate on experiments, it can apply to other kinds of experiments too, not just machine learning. So here are a couple of cool ones. So Seattle Children's Hospital built and publishes a set of COVID-19 visualizations for their own internal use, basically. And there's the team that maintains these visualizations and debugs them and reviews them. And they've been using the MLflow model registry for that, except their model, instead of doing predictions, it's just a plot or, it's just some kind of artifact that's going to be shared. And then they use that review process to check how it's doing and have people collaborate on it and also track the sources of like all the runs that went into it, which libraries were used, which data sources, and so on. So that's kind of a cool use case. And another really interesting one is Virgin Hyperloop One. So they're designing this Hyperloop train system, and they're running lots of simulations of that system to figure out the design. And they have many parameters you can put, like, how many cars are in the Hyperloop, what's the shape of each car, how many stations are along the track, all these kinds of things. And so they run a large number of simulations, and they use these MLflow APIs to query the results of all of these and get them as a nice data frame or as a table and see how they're doing. So it's nice to see this. Actually, even when we started the project, we were thinking about expanding it to just be about reproducible data science in general, and we might still do that over time. And then the final thing I just wanted to mention is use cases for reproducibility and explainability. And interestingly, this comes up a lot in highly regulated companies or organizations. So in these, you need, like, you might get asked to do an audit of something you're doing. And so you need to be able to document every piece of data and code that went into a result. And in fact, many of these, when we talk with them, have built their own custom lineage tracking systems for this purpose, because otherwise they just can't do any work at all. You might also need explanation of models. And then another really cool use case we've seen here is companies that, they need to prove to a regulator that they're using best practices as opposed to, having, like, let's say, individual people design, let's say, a trading strategy or something, or a pricing strategy that is going to discriminate against someone, or is going to use some information in an illegal way. And so a lot of them are also using AutoML here. So it's, again, this kind of hands-free ML use case where that's what they're doing. And it's pretty crazy, some of the requirements have, like, in some of them, for example, some of these government regulators, their job is to produce basically material for a lawsuit. So, like, if you find someone trading securities, for example, in an illegal way on the stock market, they need to produce a big stack of documents that then goes in front of a judge that says, here's all the evidence that this person is doing something bad, including for any automated code that found that, what was going on in that code? How do we know it's not a bug, and so on. So it's an interesting use case. Cool. So I hope that's given you kind of a sense of what people are doing.
Matei,
Yeah.
Alan seems to have a question. Alan, go for it.
Okay. Go for
Yeah,
it.
hi. I was very intrigued by the privacy example that you gave, in which you don't want to give Coke a recommendation that is based on what Pepsi has been doing.
All right, yeah.
At the same time, I was thinking universal platforms like MLflow are perfectly positioned to learn from the various separate models certain universal rules that either customer would appreciate.
Mm-hmm.
For example, not the specifics that Coke is opening a restaurant there, disclosed to Pepsi, but the fact that opening a restaurant in an area of a certain classification is a good idea.
Mm-hmm.
And I was wondering whether there is any thought towards doing this kind of abstraction, common abstraction from models that can be shared across customers.
Yeah, no, that's a great question. Yeah, I think it will depend a lot on the requirements in that domain. So, for example, one thing could be, for this product I talked about, maybe you can have a common database that says something about, like, the size of each buyer that you're selling to, or the whatever, like the the level of, like, the average income in each geographic area or something like that, and you can use that, and you can help all your customers use that site information, like use it in the models that you're training. But you've collected that information in a way that's agnostic to their kind of secret data. Yeah, I think it's an interesting question. And I think the other thing I was thinking of during your question was you might also be able to learn stuff just about, which, like, ML training runs are likely to have been successful or not across companies, and also be able to provide a better ML platform that way. That says, for example, for this, you didn't test the data on a large enough held out set, or whatever, this kind of stuff. Or, that might also be an interesting thing you can do. And then you could also do this in the auto ML case, where you're designing these models. You could still, like, you could probably learn parameters of the auto ML algorithm, or ways to tune it in each case. Yeah, it's an interesting question for sure. Yeah, and I think people are starting with very kind of simple and foolproof ways to show that what they're doing is different, but then they'll have to go up from there. Cool. Okay, great. So yeah, I had thanks for all the questions. Yeah, I had just a few more things to talk about, kind of what's coming next. So I'll just quickly flip through some of these, and then see if there are more questions at the end about what's left to do in this space. Oh yeah, I did want to show, so for reproducibility. So since this thing came up, we have in our cloud platform, we control the compute environment as well, and so we added a very simple way to take an experiment run and clone it. And we remember, so if you're developing in notebooks, we save a snapshot of the notebook as it looked when you ran it. If you're developing in Git, we store that. And we also remember the configuration of the compute cluster you were on. And then you can press this button and you can basically clone that version of the notebook and recreate that environment. So this is the kind of feature that you can build on top of this ML platform infrastructure. Cool. So yeah, maybe I'll just breeze through some recently added things. You can learn more about them online. So there's quite a bit of activity in the project. One of the sets of activity is expanding tracking for more types of things. So I mentioned before tracking for data versioning. So when you read from Delta Lake, which is this versioned storage system on top of cloud object stores, we will remember the version that you read, and then it's easy it's easy to reproduce that version of the data. So this is the kind of integration that we're hoping to build with other data management systems too. And it's just, again, we record each time you're reading from it, we intercept that call and record it. We added tracking for model schemas. So for example, a common error with models is that you change the fields that are going into it, but then the person deploying the model has not updated the code to pass the new fields. So we automatically track that, and we actually warn you when you try to move a model into a new stage and its schema is different. And then we've also added integrations with SHAP to log and compare explanations for explainability. So that's some recent work in the project. And another thing that just got announced last week actually is a collaboration with PyTorch. So the Facebook PyTorch team has been building a whole bunch of integrations of MLflow into PyTorch, in collaboration with us to do auto logging and also to use their model packaging and serving infrastructure that's more efficient, TorchScript and TorchServe. And finally, there are still a lot of questions, and there are things that MLflow doesn't cover right now. One interesting one in data management is the concept of feature stores. So this is a database that holds fast-changing data about entities, like for example, about a customer. What's the last thing they bought on the site? What's their address? What's the last time they logged on, and so on. And this is a concept where, again, people are trying to integrate this with training and inference workflows. So for example, you can train all your models at one point in time snapshot of the data. And then when you deploy them, they can be pulling in the latest data without having to copy the data out into a different system. So that's a pretty hard area. There are quite a few projects that are trying to do this. There's automatic monitoring. I think it's still wide open as to how to best do that. And then there's also, while you're doing inference, it's actually a good time to track a bunch of information and maybe see if there's drift in the data itself. Again, I don't think there's a standard way to do this, but these are all things that we're considering, developing next inside MLflow. So lots of questions. Cool, yeah. So yeah, I hope this has given you a nice sense of the concept of ML platforms and of what matters in industry. So again, in a lot of the biggest, most high value use cases in industry, you need a lot of control about what's happening and ways to fix things when applications are going wrong. And ML platforms are an abstraction to help with this. We think that the open interface design that we chose is very important for usability, but there's a lot of other ways of doing this as well. And there are quite a few problems in this space. The one other thing I wanted to mention is that if you want to see something from users of MLflow, we have a free online conference this week, the Data and AI Summit that Databricks organizes. There was also one this summer. So you can see quite a few talks on there if you want to learn more about like how practitioners are thinking about this too. So I think that's it. I'm happy to answer more questions because I think we still have a few minutes.
Great, thank you, Matei. Let's all give Matei a round of applause. Virtual world, we give you a virtual applause on Zoom. So, Matei, do you have more questions on your chat that you would like to walk through?
Let's see. My chat went away for some reason. Let me open it again.
Okay.
Huh. I see one question. How do you see the field of federated learning evolving to provide privacy? Yeah, actually, federated learning is tackling some slightly different problems from what I have here. Although the kind of the hands-free ML is certainly related to that. So part of federated learning, one version of federated learning is you have devices that the users own, and you want to send back basically obfuscated updates to your model from those, like obfuscated gradient updates. So you don't learn, you can't see which device caused a specific change. So that's being used, famously, for example, by Apple iOS. it's actually, you know, I think it's pretty specific to that consumer device use case, because for other applications, I don't know if consumers really expect that, but that could be interesting, for example, for this enterprise software thing I talked about. If you can convince enterprises that with differential privacy, it's okay for you to learn something across an industry, but you won't reveal any info about them. But, you know, I think it's still kind of a hard sell when you go to a company and say, yeah, we will use your data to recommend things to your competitors, but don't worry, like, here's a proof that they're not going to learn more than e to the epsilon, whatever, about it. So it's a little bit of a hard sell. There's another use case, which is companies, like, say, different hospitals bringing their information together and learning on it jointly. And again, I think it is happening in some cases, but it's pretty esoteric now, but it could become more and more common in the future. I think in that kind of use case also, just allowing the computation to happen at a third-party vendor is also going to be very common. So I think some of the academic work is a little like, you know, the threat model and so on is a little like far from what companies would really care about. So we'll have to see what they settle on, but there'll certainly be some use cases where they want these purely algorithmic ways to guarantee stuff. And then there'll be others where they say, like, yeah, we'll all sign a contract with this one company, and, you know, it's we're just going to let them do the work and share the stuff with us because, you know, we think it's fine to do it that way. Yeah.
Okay, more questions from the audience. So I have one on my chat, Matei. I think you kind of addressed the slide. What are the research questions and innovations here, and what does MLflow do that is different to alternative ML platforms that also do tracking?
Yeah, so I think, yeah, it's a good question. So, well, so there are, so these are some examples of like open questions. I think I talked about this. In terms of what we're doing differently, I do think compared to like all the other open source projects, at least, I think we're the only one that has this end-to-end design and that has the collaborative features around model registry specifically. So there are a lot of projects that do just experiment tracking, for example, even things like TensorBoard. And those are fine if you're just a researcher doing experimentation, but then you run into problems when there are other teams that have to collaborate. So we have this set of 4 components that are all integrated to each other. The model registry links back to the experiments. You know, the experiments show you what models were deployed based on this and so on. And it's designed for all those people to use. So I think that's one thing where we've pushed more in that direction of how does a whole company collaborate. On the other hand, you know, we've pushed less in terms of having an opinionated way to run your code. So there are platforms like Kubeflow, for example, that are all about deploying an ML stack on Kubernetes. And for us, we don't, we're not focused on making it easier to like set up a big cluster. We're focused on like, once you have a cluster, how do you manage your workflow?
Okay.
Cool. I see one question about threat models, but yeah, did you have other ones?
Not on my chat, but I have some questions.
Mm-hmm.
Do you want to?
Okay, let me just answer.
Yeah, sure. Go ahead.
Yeah, let me answer this one quickly, and then we can do yours. So the question was, what are some realistic threat models for ML in the industry? So I think one common one, so there are these adversarial settings where people are always evading you. Anything from like basically any kind of fraud type thing, you know, people putting fake reviews on Amazon, people trying to hide money laundering, all of these are adversarial. So in that case, you ultimately need like some way to just do analytics and ad hoc queries on that data. I don't think you can just sit there designing a model and say, yes, I've got all the fraud. You need to look and you need to see like, whoa, all of a sudden there are, you know, thousands of like reviews for seed packets because people are mailing seed packets throughout the US to get this to be higher on Amazon, and like, you know, do something about that. Same thing with spam detection. So I think these environments are much you need to eventually monitor stuff with humans as well if it's really adversarial. Yeah.
Okay. Great, Matei. I have a more philosophical question for you. how do you make people use new APIs when they are used to the flexibility and freedom of just ad hoc Jupyter notebooks? So what made MLflow a success in these companies? Was this because their bosses were weighing down on them, saying you have to use this for governance? This?
No, that's a great question. Yeah, you don't want to do the thing that only the boss wants, because then the users will hate it, and then it won't be successful, right? Like if you do it, the boss will eventually force them to try it, and then they'll try it for a month and they'll say, I tried it and it sucks. My productivity is terrible now. And then the boss will say, wow, it is actually really bad. I'm going to stop that. So you need something that the users like. And I think for us, one of the big things that hooked them was the tracking. So even though it looks really simple, just the ability to get all your stuff into these nice UIs, sorry, just going back, and be able to compare them and plot things was a killer feature for a lot of the ML developers. And then once you have tracking, you're set up to be able to use the other components. I think the same thing applies about model review. So like you might be surprised, but most of the enterprise, production teams we talked with, they had already been bitten in the past by these problems with bad models. And as long as you show that it's not too heavyweight and that it solves their problem, they were very excited to try it out. It wasn't like a take your vitamins kind of thing where, the doctor says it's good for you. This was like, I've been in the hospital for like 2 months in the past, and I don't want to go there again. And like, give me those vitamins.
Got it.
Yeah. Fascinating.
Related to that, where do you see this generality specificity trade-off, right? MLflow is designed to be very highly general, and that's very successful. Many of these other platform providers, like TFX, for example, I've interacted with them. They're building like optimized pipelines end-to-end for data loading and transformations within the TFX pipelines and TF serving. There are a lot of model serving optimizations people have come up with that are platform specific. How do you see kind of MLflow, will it lose out on these sorts of optimizations, or what do you see happening in the future?
Yeah, that's a great question. Yeah, so anything involving performance, I think it's hard to do that in a general way. So I think the most we can do is what I showed with the model flavors, where we can say, hey, if you do use if you have your own way of interpreting these weights and stuff, we'll let you document that, and then you can write tools or plug in tools that understand that. So we'll get out of your way. But of course, if someone goes in there and replaces the TensorFlow model with like scikit-learn, performance might fall off a cliff, and then you're stuck. So that's kind of what we did. The other interesting thing is when there are domain-specific solutions that will be even more powerful. So for example, something like search, like information retrieval or recommendation systems, there are also people building domain-specific libraries just for that, or services, like Amazon Personalize or Elasticsearch. And so for those, eventually you might want to use one of those. But the thing about enterprise ML use cases is, for many enterprises, their business and their internal data sources are unique to them. Like even the model you do at ExxonMobil versus the model you do at Shell are different because those companies just work in different ways. So there's still a lot of need for them to customize.
Got it. Okay, one last technical question about reproducibility. So in the ML systems world, there's been this whole thread of work on exploiting systems asynchrony, like, Hogwild, the synchronous parameter server. More recently, the model days with Asha and stuff like that. These sorts of algorithms are not reproducible, right? Because you run this on one machine, you run it again, you get totally different results. What do you see happening in the enterprise space? Because MLflow has such an emphasis on reproducibility. What if the ML training routine itself is unreproducible?
Yeah, absolutely. Yeah, a lot of things will not be reproducible, but it's still nice to document what went in there and to let someone run something as close as possible to it. I think if you want it to exactly be reproducible, you have to be a lot more careful. And I think some of these like highly regulated use cases have that, but in many of them, it's enough to show, okay, here's what we did. And for example, we ran it 5 times, and all 5 times it said that, we can't give you a mortgage or whatever, so we didn't give you one. It's definitely a tough problem, but it's very hard to make general computation reproducible, unfortunately. Yeah.
Okay. Sounds fair. More questions from the audience? This is very, very awesome. Thank you, Matei, for all the insights. And we learned a lot today, and getting a glimpse into real world kind of production ML concerns and how MLflow is helping meet a lot of them. This was the purpose of these guest lectures, to give the students a glimpse into what is happening in the cutting edge of industry. And certainly you folks at Databricks are really doing some cutting edge stuff. So it was a pleasure to have you. So we are out of time at this point. Any other questions for Matei about anything that he talked about?
Oh, I don't see.
On the chat, I don't see anything more, Matei.
Oh, maybe someone sent me someone said last Q, but didn't send me a question yet.
Okay. If there are no more questions, let's thank Matei again and appreciate you joining us, Matei. And stay safe, everyone. And thank you for joining this guest lecture in 291D. Take care. Thank you, Matei.
Yeah, thanks a lot.
Thank you, Matei. Always a pleasure to have you.
Yeah, thanks a lot for having me.